Welcome to the class. Dear students, today we are going to discuss on Birch reduction. In this video session, we will see what is Birch reduction, we will see the reaction, then we will see the mechanism which is of 3 steps, and finally we are going to look at the synthetic importance of Birch reduction. So let us start Birch reduction. So Birch reduction, in Birch reduction, it is a reduction in which benzene is reduced to 1,4-cyclohexadiene. Reduction in which benzene is reduced to 1,4-cyclohexadiene. This is 1,4-cyclohexadiene. As you can see, the difference between this is that these two are that hydrogen atoms are present on opposite sides of the benzene ring, or hydrogen atom is present on opposite carbon atoms of the benzene ring, right? So the reduction of benzene to 1,4-cyclohexadiene, a molecule in which hydrogen atom is present on opposite carbon atoms of the benzene ring system, is called the Birch reduction. A reduction, it's a type of reduction in which the benzene is reduced to give 1,4-cyclohexadiene, in which the hydrogen atom is added on carbon atom which is lying opposite to each other in the benzene ring system. So that is what is Birch reduction. Now let us look at the reaction. The reaction is itself before you, right? Benzene on treatment with sodium or lithium, benzene on treatment with sodium or lithium in a mixture of alcohol and liquid ammonia undergoes reduction to give 1,4-cyclohexadiene. It undergoes reduction to give 1,4-cyclohexadiene. So that is the reaction. That is what you write before the reaction, and then you give this reaction. Let me just repeat what I have said. Benzene on treatment with sodium or lithium in the presence of a mixture of alcohol and liquid ammonia gives 1,4-cyclohexadiene, a molecule in which 2 hydrogen atoms are present on the opposite carbon atoms of the benzene ring system. So that is the Birch reduction. Now you can see well the difference, the specificity, correct? You can see the difference. See, if it was a normal ordinary catalytic hydrogenation, if it is a normal ordinary catalytic hydrogenation, then what would happen? The thing that would happen is this double bond would have been broken and 1 hydrogen atom would have attached here and 1 hydrogen atom would have been attaching here. Okay, it can be here, here or here. Okay, so 2 hydrogen atoms, it will attach on adjacent carbon atoms. If it was a normal catalytic hydrogenation, that would have happened. The hydrogen would have attached at the adjacent carbon atom. Now, Birch reduction is not a normal catalytic hydrogenation. It is a selective hydrogenation. It is a selective hydrogenation at position 1 and 4. At position 1 and 4. Correct? Where hydrogen atoms are attached on opposite carbon atoms of the benzene ring. So that is a difference between the Birch reduction and catalytic hydrogenation. We can selectively go for hydrogenation of positions, right? If Birch reduction, if we apply Birch reduction, then we can selectively go for hydrogenation at specific locations. Fine? In aromatic rings only, not in aliphatic systems. This can happen only in benzene and its derivatives. So benzene and its derivatives, we can go for Birch reduction. In Birch reduction, we can go for selective hydrogenation. That is the benefit of Birch reduction. Okay, we can selectively hydrogenate opposite positions of benzene ring, right? So it's always the opposite positions of the benzene ring. So if it's a single benzene, it would be 1 and 4, right? If it is a naphthalene, then you will see 1, 4 and 5 and 8 also you will see. So they are always in opposite position. It is always in the opposite positions that addition of hydrogen takes place. That is only possible in Birch reduction. So it is a selective hydrogenation at specific locations at opposite locations of the benzene ring and its derivatives. So that is the difference between catalytic hydrogenation and Birch reduction. Dear students, now let us try to understand the mechanism of Birch reduction, because if we only understand the mechanism, then only we will retain the reaction in our mind. So we will go for mechanism. Stay tuned with me and thank you for your patience. The mechanism consists of 3 steps. Step number one is solvation of electron. Okay, electron I am writing like this. Okay, solvation of electron. First I will write the reaction and then we will try to understand. So this is sodium. We already use, it's happening in the presence of sodium, right? And there is liquid ammonia also, NH3. Now what happens is this becomes Na plus, electron goes from sodium, it dissociates and solvation occurs. Okay, solvation occurs. This is a dot, okay, indicating solvation occurs. So this is the reaction in exam. For the examination purpose, you just have to write this. Now let us try to understand what is happening here. See, what is the atomic number of sodium? Sodium atomic number? Yes, 11. So can you give its configuration? Yes. So that would be 1s2, 2s2, 2p6, that is 10, and 3s1. Am I right? Yes. So how many electron does it need to get rid of to attain octet configuration? You are correct. It needs to get rid of this electron. Correct? It needs to be 3s0. Okay. So that is why it is getting rid of this electron. Right? And now it has attained octet configuration in its second shell. Octet configuration in its second shell, or you can say it has attained the atomic number of 10. 10 is the atomic number of nearest inert gas, which is neon. Okay, so you can say that sodium actually loses one electron to get octet configuration in its second shell, which can make it stable. Or you can say in other words that it does so as to attain the inert configuration of the nearest inert gas, which is neon. So by attaining this configuration, it becomes stable. So for sodium, it is a stable kind of situation. If sodium dissociates, it becomes Na plus, it becomes stable. Correct? Now let's forget about this sodium. Now for the time being, let us look at electron. See, for the electron, it is a particulate matter. It is a particulate matter with a unit negative charge. Only one negative charge is there. So it has this unit negative charge, this electron, it has a tendency to get attracted to opposite charge, or it has a tendency to get attracted to nucleus. There are two nucleuses here. One is sodium nucleus, right? The nucleus of sodium, which is this, and there is another nucleus which is NH3, right? This is also a nucleus. Now electron, it would never get attracted to sodium nucleus. Why? Because sodium is electropositive in nature, and we have already shown why it is electropositive, right? Because it wants to attain octet configuration in second shell, right? We have already seen that it wants to attain inert configuration of neon gas. So it tries to take out its electron, and that is why sodium is electropositive. So now when the electron has come out of sodium, it would never go back to sodium because sodium is electropositive in nature. So a better option for the electron is to get attracted to nitrogen, because nitrogen itself, it is an electronegative nuclei. Okay, the nucleus of nitrogen is electronegative. It tries to attract electron. Electron also tries to have a pull on nitrogen. So it is a win-win situation for both the nitrogen and the electron, right? Electron also tries to pull the nucleus of nitrogen, and nitrogen, because it is electronegative nucleus, it is also pulling the electron. So it tends to get loosely associated with nitrogen of ammonia. Now this is not for only one ammonia molecule. There are so many ammonia molecules, because ammonia is the solvent here. It is liquid and it is the solvent here. So a lot of NH3 molecules, it gets loosely associated with this electron, right? A lot of ammonia molecules would get loosely associated, okay, because NH3N is electronegative. It pulls the electron towards itself, and electron has a unit negative charge. It pulls the nucleus of nitrogen towards itself. So what could happen? All ammonia molecules would come and surround the electron. There is no bond formation, just it gets loosely associated, right? By this way, electron's negative charge somewhat it gets stabilized. The negative charge on the electron, it somewhat gets diminished, okay, its intensity decreases, it somewhat gets stabilized. So for electron also, electron achieves a stabilization, right? Stabilization by solvation. This is solvation. What is solvation? The solvent molecule, when they surround an entity, that phenomena is called as solvation. Okay, it can be any atom, or it can be any group of atoms, or it can be a single electron. So when solvent molecules surround an entity and stabilize it, that phenomena is called as solvation. So here solvation is actually taking place. All the solvent molecules, they decrease, they surround the electron. Not only do they surround the electron, they decrease the negative charge on the electron. They diminish the negative charge on electron, thus stabilizing the electron. So solvation effect is happening. By solvation, electron is getting stabilized, right? Somewhat its negative charge is decreased because of solvation, because the negative charge is being distributed to all nitrogens. That is the reason. So somewhat the negative charge is getting decreased, electron is getting stabilized. So for electron it is okay, good situation. Okay, in reaction we don't show it like this. Okay, in reaction we just show it like this. So you have to show it like this. So as I was saying, for electron it is a okay situation, it attains stability by solvation. And for sodium also it is a good situation because it attains the inert configuration of the nearest inert gas, which is neon. So the reaction will, of course and definitely, it will propel forward. This reaction will propel forward, there is no issue. It is thermodynamically stable than the reactants, right? This portion is thermodynamically more stable. Fine. So now the electron is there. Let us go to step number 2. Let us go to step 2, which is formation of benzene free radical. Formation of benzene free radical. So first I will write the reaction and then we will try to see what actually happens. We will explain. Okay. Formation of benzene free radical. So here what happens? There is benzene. Okay. So this is that, and electron. I draw all hydrogens. Each carbon atom is having one hydrogen atom. In benzene ring, I draw all those hydrogen atoms for better understanding. Now again I write the benzene ring like this. Okay, and the electron comes here, it attacks this position. So when the electron comes here, just let me shift the bond. So when the electron comes here, what would happen? This pair of electron would face repulsion and it would come here. Okay, and this would come here. I will explain everything to you. So this is a pair of electron, negative charge. So now I am almost done with the reaction. Almost done. Yes. So now we will try to understand the reaction. I am almost done with it. Okay. Thank you for your patience. Now, as I said already, the electron is not bound to solvent molecule. It is just loosely associated with solvent molecules, right? Somewhat electrons negative charge has diminished somewhat. So it is not a permanent resort for stabilization. It is just temporary resort for stabilization. The electron will be actually stable when it gets associated with a molecule like benzene. Okay, then only it would get actual stabilization. So what electron does is to dissociate from its solvating effect. It comes out of the solvent, it dissociates from its solvent solvation effects, and it attacks benzene ring. It attacks benzene ring. Now the question is, at which why it attacks the benzene ring? That is a question. And why should it attack carbon? Why not hydrogen? This is the question. Dear students, see, electron, it just wants nucleus. Okay, it just wants nucleus. So there are 12 nucleuses here. Two kinds of nucleuses are there. One is the carbon nucleus and one is the hydrogen nucleus. Which nucleus electron will attack? The answer to this question is, it will attack the more powerful nucleus. Which is the more powerful nucleus? That which is having more number of proton is more powerful. See, carbon is having 6 protons. Hydrogen is having only 1 proton. So the effect of 6 proton in attracting an electron is more. So electron will attack the carbon, not the less powerful hydrogen. It will attack the carbon, all because carbon has got 6 proton in its nucleus and it is better able to attract the electron. So electron will attack carbon. Now there are 6 carbon. Which carbon electron will attack? See, it can attack any carbon. It can attack any carbon. Whatever carbon it attacks, that position will become first position, because benzene is ultimately a ring structure. So whatever position it can attack here, it can attack here, it can attack here, here or here. Whatever position it attacks, that position becomes number 1, because benzene is nothing but a ring system. So of course here I am, for the method of convenience and for better understanding, I am attacking, making it attack this position. Okay, so if it attacks this position, what would happen? See, if it attacks this position, this electron pair will face repulsion, this one, and it will come to adjacent carbon-carbon bond. It will come to adjacent carbon-carbon single bond. So it comes here. So when this pair comes here, this carbon, what is the maximum number of electron that a carbon can hold in its orbital? Yes, you are right. In its second orbital, it can hold 8 carbon atoms. Okay, it doesn't have a 3s shell. There is no 3s orbital. So what would happen when this comes here? Here this carbons 8 electron were already satisfied. Okay, it had octet configuration, but when it comes here, because carbon doesn't have a 3s orbital to accommodate this pair of electron, this pair of electron actually goes here. Okay, now this pair of electron has come here in this. I hope you understood this. When this electron comes here, this pair faces repulsion, it comes to adjacent carbon-carbon positions. When this pair comes here, this carbon atom, it doesn't have 3s shell to accommodate 10 electron, right? It can only accommodate 8 electron, and that too in its second shell. So what would happen? This pair would come here. Okay, and this pair is accommodated in this carbon atom. I hope you are clear. Now when this electron comes here, what it would become? Yes, you guessed it right. It becomes a powerful carbon anion. What it would become? A powerful carbon anion. Right? A carbon anion is a powerful base. It acts as a Lewis base. A Lewis base is that which can donate a pair of electron. So it acts as a very powerful base. A carbon anion is a very powerful base. Such a powerful base that alcohol is a weak acid. Actually, alcohol is a weak acid, but it behaves like a very good acid when it sees a carbon anion. It behaves like a very good acid. So here alcohol acts as Bronsted-Lowry acid. It gives its H plus, right? So when the H plus comes from here, it dissociates from here, and when the H plus comes from here, it leaves its pair of electron with OR, and it comes with its empty s orbital. and it accepts the 2 electron in its empty s orbital, thus attaining duplet configuration, or thus attaining the configuration of its nearest gas, which is helium. Also, it makes a bond with the benzene ring. So here we get benzene free radical. It's called a free radical because the electron is here. Benzene free radical. So that is the second step. I hope you got this second step. Now let us now understand step number 3. I hope this is clear to you, how it came here and how this electron pair acted as a carbon anion. It's a carbon anion. It acts as a very good Lewis base, that even a very light and very weak acid like alcohol, before carbon anion it would act as a very strong acid. It acts as a Lowry-Bronsted acid. H attacks here. H comes with its empty s orbital, accepts these 2 electron in its orbital and becomes all this we have said, right? And this is the product that we get. Now let us go to step number 3. Step number 3. The duster fall off my hand. Okay. Step number 3. Please write here step number 2. Okay, it skipped from my mind. Step number 3. Let us see what it is. Formation of 1,4-cyclohexadiene. Formation of our product, nothing else. Formation of, what is our product name? 1,4-dihydro, or you can say 1,4-cyclohexadiene. Let's see what happens. Now we have to start from benzene free radical, right? So here is the benzene free radical. Sorry, this is the situation. Am I right? Yes, fine. Now another electron comes and attacks at the same position. Same situation occurs. And this results ultimately. So I am writing the reaction first so that I can make you understand what is behind this. I am not written all hydrogen atom. If you want to write, you can write. There is no need to write now all hydrogen atoms. So this is step number 3. This is where we stopped in step 2. Benzene free radical. Okay, there we have attached all hydrogen atoms. Here I am not attaching. Now what is happening here? Another electron gets dissociated from loose attractions, loose solvation effects of ammonia. Another electron it dissociates, and that electron it now tries to attack carbon atom. Now the question is, which carbon atom it would attack? Which carbon atom it would attack? For that you have to see whether the 4th valence of carbon is completed in all carbon atoms. Okay, so let me write this. You have to see that whether carbon atom is attached to 4 other atoms through single or double bonds. Okay, so let us look at this carbon atom. Is its 4th valence complete? Yes. This carbon atom is attached to another carbon atom here by single bond. This is the second one, this is the third one, and this is the 4th one. Look at this carbon atom. Is its 4th valence? Can you account for its 4th valence? Yes. 4 valences are accounted. See, 1, 2, 3, 4. Look at this carbon. Yes, 1, 2, 3, 4. Look at this one. Yes, 1, 2, 3, 4. Look at this one. Yes, 1, 2, 3, 4. So 4 valences are accounted for all the carbon atoms. But we have not seen this one. We will see this one. Just look at this one. How many atoms this is attached to it? 1, 2, 3. Only 3. So the 4th valence is not accounted for this carbon. That only means that this carbon has extra positive charge. it can easily accommodate one more electron. Okay, compared to all other carbons, this carbon has extra positive charge because it is not completed its fourth valence. Its fourth valence is empty, right? It needs one more electron here. So it is comparatively much more positive. So the electron will attack only at this position now. No other position it will attack. So now when it attacks here, the electron pair comes here. Again this becomes a carbon anion, and as we have seen earlier also, a carbon anion is a very strong base. So strong that even a weak acid like alcohol, which is actually weak, it acts as a strong acid because of the presence of this powerful base. And it acts as a Lorry-Bronsted acid. H plus is dissociated. When H plus is dissociated, as I said earlier, it leaves its pair of electron with OR minus, comes with the empty s orbital, accepts the pair of electron in its empty orbital, and attains the configuration of helium, or it attains duplet configuration. Also, it makes a bond with the benzene ring, leading to the formation of our product, which is 1,4-cyclohexadiene. 1,4-cyclohexadiene. So that is how we get 1,4-cyclohexadiene. I hope it is clear to you. I hope the mechanism part is clear to you. Let us now come to synthetic importance. Synthetic importance. I am going to draw three compounds on the board, not things, pardon me, three compounds on the board, and then we will see its uses. All of these three compounds we can make through Birch reduction. The first and the most important is this. Okay, this is 1,4-dihydropyridine. 1,4-dihydropyridine. Okay, now we can make 1,4-dihydropyridine using Birch reduction. When we are doing Birch reduction in pyridine, this is pyridine. If you are doing Birch reduction in pyridine, it becomes 1 and 4. Here one hydrogen will get attached. Here already one hydrogen is there. This is of pyridine. Here one hydrogen will get attached, and here one hydrogen will get attached, right? And it will become like this, right? Lone pair is still with that, Okay, so now this would be the situation. Here lone pair I have forgotten to put. So this is 1,4-dihydropyridine. So it is a basic moiety in many drugs. I will write down the drugs in which you will find this 1,4-dihydropyridine structure. Okay, the first is amlodipine. Amlodipine, you might have heard its name. Okay, nicardipine. Okay, nifedipine, nimodipine, phenodipine. If you are seeing the structure of all these drugs, you will find this structure as the basic moiety. Okay, that is a basic moiety in all these drugs. What are these drugs used for? Actually, they are calcium channel blockers. Calcium channel blockers. So they are used as antihypertensives. They are used as antihypertensive drugs. So you can make antihypertensive drugs, that is, you can make calcium channel blockers, these 5 drugs, right, containing this by Birch reduction. By Birch reduction. So that is a very big synthetic utility of Birch reduction. Let us go to our second compound. Let us go to second compound. Okay. So for the second compound is like this. Okay, this is naphthalene. Okay, this was naphthalene, and now this is 1,4-58 tetrahydronaphthalene. 1,4-58 tetrahydronaphthalene. Naphthalene. Okay, this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so one hydrogen has added here. There was one hydrogen here of naphthalene, that is original hydrogen, but one hydrogen has got added here. Similarly, one hydrogen has added here, one hydrogen. This was already present in naphthalene and one hydrogen got added here. This one was already present and one hydrogen got added here. So what we get is 1458 tetrahydronaphthalene. Now what is its use? It is used in dyes, it is used in paints, it is used in as lubricants, and it is used as a high boiling solvent. High boiling solvent. These are the 4 uses of this. So it is used basically in the paint industry. Okay, in the paint industry. Dyes, paints, as lubricants, and as high boiling solvents. So this is the second important compound that we prepare by Birch reduction. Let us go for the third compound that we prepare. You know this compound we have studied in our third semester. We studied in our third semester B Pharm course. Yes, you guessed it right. This is phenanthrene. Okay, here also actually there was a double bond, but after Birch reduction this double bond has gone. Okay, so one hydrogen is added here and the other one is added here. So now this is 9,10 dihydrophenanthrene. 9,10 dihydrophenanthrene. So if you ask me what is the use of 9,10 dihydrophenanthrene, I would say that presently there is no use, but in future we are expecting. Why we are expecting the use is 9,10 dihydrophenanthrene, it has got a range of activities, a range of biological activity. It has got analgesic activity. You know, it is used for stomach aches. It is effective for stomach ache. It is used as anti-allergic. It is used in cough. So it means it is anti-allergic activity. Then it is used as anti-inflammatory. It has shown anti-inflammatory activity also. And you know what not it has shown? It has shown anti-hypertensive activity. Anti-hypertensive activity it has shown. Analgesic, cough, anti-inflammatory, antioxidant activity also it has shown. But there are no drugs that actually have 9,10 phenanthrene. Now there is an issue. The effectivity is less. That is the issue. It shows this activity, but the intensity of activity is actually less. So this is because we are having some stereochemical issues. Okay, when we are taking it inside our body, this molecule is not effectively binding with the receptor. So there are some stereochemical issues which are being seen into, and hopefully it will be modified. This moiety will be modified and we will get good potential lead candidates out of this molecule that is having effective activities like these. So it is a molecule, it is a compound under research. Dear students, I hope you have understood and liked the class. This class we have discussed so many applications of Birch reductions. Also we have seen the reaction and mechanism. If you have liked the class, please do not forget to like, share and subscribe this channel. Your support means a big encouragement for me. Thank you very much.